Multicast is one of those technologies where you either work with it daily in production or you don't. But on exam environments, there's absolutely no escaping multicast routing. And here's the thing, throughout our journey, throughout this playlist, we've seen multicast a couple times when we talked about how neighbor adjacencies between IGPs form, like OSPF or EIGRP. But now we're going to take our multicast routing skills up a huge notch, where we talk about how to actually design multicast networks and environments for the enterprise. Now, multicast can be a pretty complicated topic, especially if you're brand new to multicast. So what we're going to do in this skill is set up just the foundational principles of how multicast operates before we actually jump in and talk about the design and protocols that are used within multicast. That's what the next skill is going to be all about. So in this skill, enjoy it as we get used to how the foundations of multicast really work in an enterprise environment. Let's get going. The first question that we should answer is, why multicast? Why does multicast exist? What problem does it really solve? And how should we design our networks with multicast in mind? What is the scenario where we would think, multicast may be a better use case in our enterprise than something else? That's what this nugget is all about. It's just to set up the principle of what multicast does at the end of the day. Let's get going talking about where multicast fits in the big picture of our network. Now, before we jump into this topic about what multicast does, we need to introduce you to the lab that I'm going to be using throughout this particular skill and the next skill. We're using the same enterprise lab that I've used throughout previous nuggets in this playlist, and I'm focused in on just the bottom half, everything below this black line here. And what I've done is I've deployed OSPF throughout the environment. This is actually really important to have an underlay in an IGP operating, sharing routes, but that's going to be a reason or a topic that we talk about in a later nugget, particularly when we get to reverse path forwarding. Just know that for now, I already have IP addresses assigned on all of these devices and routes are being shared throughout the environment. Beyond that, I am performing summarization on these distribution switches as advertisements leave the area and go into the core backbone area. So we summarize these prefixes that you see listed right here on the screen as they're advertised out of the area. We do have end-to-end reachability, so this desktop host right here can ping this desktop host right here if that's what we want to do. Now, to go a little bit forward and talk about how multicast would work within this environment is a pretty important topic to talk about. First, recall what unicast routing does. This is kind of a big thing. A unicast route is all about one IP address or one device or one node communicating to another direct IP address or node. In this case, if this host wants to ping this host, it would form a unicast packet, which would be routed throughout this network, something like this, until it reaches its direct endpoint. This is a one-to-one communication. Now, what about the broadcast? Broadcasts are typically used on Ethernet segments. They don't really go beyond a router. So desktop 25 here could send a broadcast frame or packet into the switch, and it would be sent out all other switch ports that are communicating on the same VLAN. In this case, I don't have trunks going up towards the distribution. These are layer 3 routes. So a broadcast frame from desktop 25 would be restricted to the VLAN that's on that access switch. But the point of the broadcast is it is a one-to-all, but it is contained within that layer 2 Ethernet segment. What happens, though, if desktop 25 wants to stream data to multiple resources throughout the entire enterprise? Pretend for a moment that desktop 25 is starting a video conference, and it wants to be the source. Just like I have this camera right here in front of me, pretend for a moment that I want to stream this video feed right now throughout the entire enterprise. That's the idea that we have here. So we have one source going to many destinations. And beyond that, we don't want to restrict it to just our VLAN. We want it to go throughout the enterprise to however many resources want to receive my video stream. This is the point of multicast. This is multicast in action. So maybe we have a host here on switch 11, and maybe we have a couple hosts here on switch 12, and maybe we have no hosts on switch 13. The idea is that desktop 25 here could send its stream into the network, while these hosts over here could make a request that they want to receive that stream. And then all of our network devices work together in order to coordinate how a source can send a stream of data into the network and how our recipients that want it can actually retrieve it. There are many different flavors or styles or ways that we can efficiently deploy this throughout the network because multicast has been around since the 80s and it's evolved a lot. So there are a bunch of different design techniques that we're going to be talking about over the next couple skills. It's just really important to set up the fundamentals of multicast first. So that sets up the fundamentals of multicast. There's a little bit more that we need to talk about before we move on. Recall from our IPv4 addressing scheme that the Class D block of addresses is reserved for multicast addresses. And this was specifically the 224.x.x.x through the 239.x.x.x block of addresses. This is reserved for multicast address. And we've seen some of these multicast addresses already, haven't we? In OSPF, there's 224.0.0.5 or 6. In EIGRP, there's 224.0.0.10. Another popular multicast address is 224.0.0.2, which is the all routers multicast address. Now here's the kicker. Think for a moment about the actual behavior about these multicast addresses that we've just laid out right here. If we enable EIGRP, for instance, on switch 7 and switch 6, they start communicating multicast packets destined for 224.0.0.10. So switch 7 sends a hello packet out this way, and switch 6 here sends a hello packet out this way. But notice something interesting. Switch 6, upon receiving a hello packet, will not forward that packet towards the other switches. That's because this is actually by design. There is an RFC out there that specifies the 224.x.x.x address space is reserved for multicast addresses, but only on the Ethernet segment that they're sent on. In other words, 224.x.x.x addresses should not be forwarded by routers. The idea being that we could send a multicast packet from one device into a switch that maybe has multiple devices on it, and all of those devices on that Ethernet segment could hear it, but it wouldn't be forwarded beyond that. That makes perfect sense when you think about OSPF or EIGRP neighbor adjacency formation. We only want a neighbor adjacency to be formed on the interface that we enable it on, right? We wouldn't want EIGRP to forward an EIGRP hello packet to the next neighbor, and then we accidentally have neighbor formations coming to life. That would be bad. But in our original scenario, what were we talking about? We were talking about desktop 25 sending a stream in of multicast traffic, and then these routers or switches that are performing routing capabilities are forwarding that multicast packet throughout the network. And that's why we call this multicast routing. This is a big deal. We have to now have a multicast routing table, just like we have a unicast routing table. That way we know when a multicast packet comes in, we know where the next hop should be. We know exactly where to forward that multicast packet. So you should know that when you see these 224 addresses, typically they are not forwarded from one address to the next. Now they can be, but they're typically not. That's what the RFC states. However, if you saw a 231.x.x.x address, now's when we would start looking into our multicast routing table and seeing where all traffic can be sent or forwarded, who is sending traffic to that address, and who is expecting to receive traffic from that address. That is the idea with multicast routing. The key word there is that routing. This is the thing that throws people for a loop the first time they actually deploy a multicast network. So this sets up the point of multicast routing. Through the next couple nuggets, we're going to talk about how it actually works within an enterprise network. I hope this has been informative for you, and I'd like to thank you for viewing. Now it's time to actually start transitioning into seeing multicast in action. We're going to talk a little bit about a protocol called IGMP, and this is where our multicast network really starts to be formed. But we're not going to dig deep into IGMP and the different versions of IGMP. That's what the next skill is all about. For now, we're just setting up how a multicast stream is initiated in the real world, and that begins with an IGMP. Let's go. Welcome to Multicast Routing, because this is the part where we turn our skills up a huge notch if you're brand new to multicast routing or multicast routing design. What we're going to be introducing now is how a multicast network is actually formed. And there's two protocols that are typically in play here that make multicast routing come to life. Now, before I go any further, know that the next skill is going to be all about digging deeper into how these protocols are actually deployed and designed, because there's many different flavors and variations and styles of it. But the idea at the end of the day is we have these two protocols. The first one is IGMP. Let's talk about what IGMP does before we move on to the second protocol. With IGMP, what we're doing is we're initiating a multicast stream or a request to receive a multicast stream. So let's take this desktop device down here at the bottom of the screen for just a moment. Let's say it's expecting to receive a multicast stream. Let's say it wants to receive a multicast stream from a made-up IP address like 231.1.1.1. In multicast, they call this a group. It wants to join the multicast group 231.1.1.1. So communicating at layer 2 and layer 3, the idea with IGMP at the end of the day is that this desktop right here will send a request in to its gateway or its multicast participating router and say, I would like to join this group. Again, I can't stress it enough. It's important to know that there's a group there, because when this multicast participating switch right here, its default gateway, receives it, it's going to register that it needs traffic destined to that group. So it saves this in its routing table as a star, comma, G, which is a group. Literally, it's written out as star, comma, 231.1.1.1. How do we interpret this? What does that star even mean? Basically, what we're saying here is the source of anywhere and the group that it's participating or listening on. All we've done up till this point is made a request to join a group. We haven't talked about where that traffic is actually coming from yet. So all this device knows about at this time is that it needs group traffic or traffic destined to 231.1.1.1. On the flip side over here, we'll look at this desktop and say that it wants to initiate the stream of traffic to 231.1.1.1. So it will begin streaming in its data along with an IGMP request letting it know that it wants to begin streaming in this data. This device will now, instead of having any source destined for this group, will have an entry for 192.168.1, let's say this is 25 because this is desktop 25 after all, comma, 231.1.1.1. So over here on switch 7, we have a source and a destination group, and over here on switch 14, we have a request for any source destined for 231.1.1.1. This sets up the initiation of multicast within our enterprise network, and this is what IGMP does. IGMP is all about initiating a request to our local router that we would like to receive or send data to or from a multicast group. So now the question becomes, how does traffic get from here to here? And this is where we introduce the second protocol called PIM. PIM is basically a multicast IGP. That's the best way that I could explain it, is it's just like EIGRP or OSPF, but for the multicast world. As long as all of these devices through our topology have PIM enabled on their interfaces, they will form PIM neighborships. And PIM will exchange information about we have a source for this group and we have a request to receive this group throughout the topology. Now, how it actually builds the path is going to be very, very tricky, and that's what the next couple nuggets are all about. For now, you just need to know that IGMP is how a local host forms a request or a stream to its local router, and then PIM is how information about that stream is propagated throughout the actual enterprise itself. You also need to drill into your head the concept of star comma G, or over here we have S comma G, a source and a destination group. And you need to really get familiar with the fact that a multicast address is oftentimes referred to as a group because we have a group of devices that are participating within that multicast address. So this sets up how IGMP and PIM actually operate under the hood. I hope this has been informative for you, and I'd like to thank you for viewing. Now's the part where we jump our multicast skills from here all the way up to here, because what we're going to begin talking about is the tree formation. Just like spanning tree has a tree that kind of forms and finds a best path from point A to point B, so does multicast. But there's a bunch of different flavors of how trees are actually formed within multicast. So what we're going to set up in this particular nugget is how the source tree is formed to allow the best path from point A to the destinations that we're going to be talking about. When we say source trees, what we're really talking about is the shortest path tree. It's important to know that those are synonyms. They are interchangeable, and you may see either one of those on an exam environment. So let's talk about what the source tree or the shortest path tree really does in a multicast enterprise network at the end of the day. Let's go. So in the last nugget, we introduced a lot about the formation of an enterprise multicast network, and we've actually seen now how multicast routing comes into play. We have a multicast packet that needs to be routed from one router to the next, and we talked about how PIM is what sets us up to do that. But here's the thing. PIM has evolved a lot over the years, and there's many different flavors of it. We're going to talk about those in depth in the next skill. For now, the next concept we have to understand is how the path from the source to the destination can actually be formed, and this is by using trees. Now, there's really, at the end of the day, two different kinds of trees, the source tree and the shared tree. The source tree is often also referred to as the shortest path tree, or sometimes even abbreviated to the SPT. If you're reading textbooks, you're no doubt going to see SPT written a lot. Let's talk about how the source tree works. The idea with the source tree is that we are expecting that we have lots of clients located throughout our enterprise, all who want to receive this traffic. So the idea that we're going to do here, since all of our clients are densely populated, that is a key word to understand in multicast, is dense. Since we're expecting all of our clients that want to receive the stream to be densely populated, what PIM is going to do in this particular design is it's just going to forward the traffic out, and all of the PIM participating in routers are going to, by default, forward the traffic to all PIM participating interfaces in the entire enterprise. And it's going to look like this. It's just going to keep going and going and going, and you get the idea until basically every single line here has been forwarded out. The way these switches now behave is they will see the S, G. All of these switches down here that have initiated their IGMP request, they will see the source of 192.168.1.25. That was the host address right here for this desktop. And the destination we said was 231.1.1.1. What they'll then do is look in their routing table and find the shortest path to 192.168.1.25. So let's pick on switch 8 here. Let me clear the screen just for a moment. If we're picking on switch 8 here, and there's a host that wants to receive the stream from this device, the stream is going to come in to both switch 6 and switch 4, and then come back down to switch 8. When switch 8 looks in its routing table, it will see one or maybe two equal cost multipathing routes towards that subnet. Let's pretend for a moment that there's just one route towards this subnet, and that's going to switch 6. What switch 8 will then do is it will send a prune request back to switch 4. It will say, remove me from your multicast route, and therefore the stream will exist in this direction, because switch 7 will still continue to forward the data to switch 4, but switch 4, having received the prune request, will not send it back towards switch 8. In other words, switch 8 has determined that the shortest path to the source is this route, and that's what makes it a shortest path tree. The receiving destinations will look in their routing table and find the shortest path towards the source, and then send prune requests towards all of the other sources that it learned from. Here's the pros and cons to this. The pros are it's very easy to deploy. We simply just turn it on, and the network will figure out the shortest path towards the destination. And the cool thing about that is we get very efficient routing at the end of the day. Our receiving nodes will only get the data via the shortest path towards the source itself. The problem, though, is that the traffic will be sent out every interface to every device. And unless all of these devices are expecting to receive this multicast traffic, there's going to be a lot of an overhead for these network devices to process all of this traffic that they don't need. For instance, in this scenario, if I only have one source and one destination, do I really want my multicast traffic going out every single interface and up into the core like this? No, that's going to be a huge burden to us. So this is where the problem with source or shortest path trees comes into play. And really what we're talking about is something called PIM dense mode, which is what we're going to cover in the next skill. This really only works when they're densely populated and we need to flood this traffic out everywhere. So this has been understanding what the source tree or the shortest path tree is all about. It's about sending the data out everywhere, and then the devices find their shortest path back to the source. I hope this has been informative for you, and I'd like to thank you for viewing. So in the previous nugget, we set up the source tree, or the shortest path tree, that was all about understanding if our devices or our endpoints that want to receive this stream are densely located throughout our enterprise network, and they find the shortest path towards the source. Now, what happens in a scenario where they're not densely located throughout our network? Maybe they're sparsely located, only a couple of endpoints want to receive it. What we then use is something called a shared tree, and this is where we're introducing some new topics. And the spoiler here is that this is actually what's more popular to deploy within our networks for a few different reasons. Let's talk about the other type of tree-based solution called the shared tree that could be used in a multicast enterprise network. Let's get going. In the last nugget, we set up the topic about how the source tree works and how it sends data everywhere, and then the devices who want it will receive it and find the shortest path back to it, or the devices who don't want the traffic or don't want to receive it on a specific interface will send in a prune request. In reality, what we're really describing here is something called PIM dense mode, which is what we're going to be covering in the next skill when we set up the difference between PIM dense mode and PIM sparse mode. They just implement trees differently from each other. That works okay in an environment where we're expecting a lot of different devices to receive this traffic because they're densely populated throughout our entire network. But what about the scenario where we had only one source and one destination? We had this S, G over here, and then the single star, G over here. If you look at every single link that's on this network here and then start to consider that it could be flooding a stream of video traffic, like video gaming streaming. What if I'm streaming a 4K video game from this? That's a lot of bandwidth utilization to now go to all of these devices that don't have a receiving host attached to it, and that could be a big problem. What we could end up doing is actually set up a centralized location to send or receive this particular traffic. So let's pretend for a moment that we want switch 1 to be this centralized location for sending or receiving this traffic. This is called the rendezvous point. In almost every documentation, you'll see it abbreviated to RP, but this is the rendezvous point. The idea is that a sender will by default send its traffic directly to the rendezvous point, and receivers will send their request to receive to the rendezvous point. Do you see what's happened now? Now all of a sudden my multicast stream takes a direct path to this rendezvous point. Is this the shortest path possible? Maybe, maybe not. For instance, if I had moved my rendezvous point all the way up to switch 15, well, now it's definitely not the shortest path possible. We're taking one hop extra up in order to get to it. But this is called the shared tree. And why is it shared? Because now we can set it up to where multiple groups, like 231.1.1.1 and 232 2.2.2.2 could be coordinated from the same rendezvous point. You could also configure it to have multiple rendezvous points for multiple groups if that's what you wanted to do, and that's a topic that we'll get into in the next nugget. For now, the idea that we want to set up is in the environment where we don't have as many listeners waiting for a multicast traffic, we may want to explicitly configure where traffic should be sent and where traffic should be landing on, or a request to receive traffic should be landing on at a rendezvous point, and this is how the shared tree actually works. Now, there's some Cisco-specific nuances to this, and especially when we start digging into the PIM protocol in the next skill, we're going to talk about how these all work together. But for now, this is just understanding a different style of sending and receiving traffic out from a source to a group. This is the shared tree. I hope this has been informative for you, and I'd like to thank you for viewing. In the previous nugget, we introduced the concept of rendezvous points when we were talking about the shared tree. Now, here's the real thing. If you grab nothing else from the skill, grab this bit of information, that the majority of your multicast design and manipulation is going to be built around this rendezvous point and how it's used within the shared tree. What we need to talk about in this nugget is how different types of rendezvous points can be deployed, whether they can be deployed automatically with discovery for different groups, or if we manually or statically set the rendezvous point. Let's get going talking about the different styles of rendezvous point deployment. Here's the thing, rendezvous points are really important to nail down and understand when it comes to multicast routing, because this is one of the biggest design implications that you can have, is where should source traffic be sent to and where should request information be sent to, and then how they can figure out how to get to each other from there. It all comes down to the rendezvous point. Now, in the previous, we've been talking about a sample scenario where we have an S, G of 192.168.1.25 and a group of 231.1.1.1. If we're going to go the shared tree route and we want to define a rendezvous point, we need to know that there are a few different ways that we could actually design our rendezvous point. First of all, we can put our rendezvous point effectively anywhere within the entire enterprise. It's not mandatory to put it in a most centralized location, although you could see some bandwidth utilization benefits from doing so. So the first method of creating a rendezvous point is to simply statically assign a rendezvous point. You should know that you can statically assign a rendezvous point for all groups as well as for specific groups. So I could create switch 1 here to be the rendezvous point for every single multicast stream that could exist within my environment, or I create the rendezvous point for specific groups by identifying them with an access control list. There are some obvious benefits here that we have a lot of administrative control over which group gets which rendezvous point, but there's also the drawback that there is a lot of administrative overhead that we have to assign a rendezvous point for each one of these groups or keep up with this rendezvous point throughout the environment. What may be better for us is to use some sort of automatic RP mechanism that can automatically identify rendezvous points throughout the entire enterprise. Cisco created the technology called AutoRP. What a clever name. And it is Cisco proprietary. The idea here is that on our rendezvous point, we can again tell it, you are the rendezvous point. And you can tell it is going to be the rendezvous point for all groups or the rendezvous points for specific groups that are identified by ACLs. From there, this particular rendezvous point will make a RP announcement that will announce to the entire enterprise, I could be the RP for a specific group or all groups. There then becomes a mapping node, which in many cases is often the exact same node that helps these other devices throughout the enterprise perform RP discovery. The idea now is that when desktop 25 sends in its IGMP join request, and that is creating a star comma G on switch 14, now if we've configured switch 14 to be using a shared tree structure, we don't have to actually statically configure the rendezvous point address on this device. it can perform the RP discovery, which could automatically point it straight to the rendezvous point. So in a very large enterprise where we could have hundreds of devices, rather than manually configuring the rendezvous point throughout the entire enterprise, we could use auto RP on switch 1, for instance, and then let the discovery of the rendezvous point take care of itself from there. But like I said, auto RP was the Cisco proprietary mechanism. There is an industry standard mechanism that does effectively the same thing, and that is bootstrap router configuration, or BSR. It does effectively the same thing. We announced that this is the bootstrap router candidate, and then the discovery mechanisms take over from there, and they still find the rendezvous point. In my honest opinion, the BSR is easier to configure on Cisco devices anyways, but both of them bring unique ways to handle the same situation, is that when we have a shared tree, we don't now have to statically configure the rendezvous point throughout our entire enterprise. We can create a rendezvous point and let discovery take place using auto RP or BSR. So that's understanding rendezvous point placement and different styles of configuration with discovery. I hope this has been informative for you, and I'd like to thank you for viewing. Now, one of the things that you as a network designer need to think about is scalability and stability. There's a big part about stability when we talk about loop prevention. Multicast has the potential for loops if it's not deployed correctly. But luckily, there's a mechanism built into most multicast networks called reverse path forwarding checks. And the whole point of this nugget is to understand how RPF can actually be used to scale and stabilize our network so that we don't create multicast loops. Let's get going talking about how RPF checks play a big part of how our network multicast design is actually laid out. Our final topic to talk about in multicast design is how it's actually going to create a loop-free topology. Think about this for a second. We have this S, G right here, right? This is our source, and it sends multicast data into the environment. And if this is a densely populated environment, maybe what we would do is we would forward the traffic out all interfaces. Then we forward the traffic up to this interface, who forwards the traffic over to this interface, who forwards the traffic back to this interface, who forwards the traffic back. Uh-oh, do you see what's happening here? We're going around and around and around and around, and this becomes a major problem because we could very easily create loops with multicast traffic if we're just forwarding traffic nonstop in a densely populated environment. So what we implement by default, what happens behind the scenes without us intervening at all, and something that you should know that's very important, is the RPF check. As traffic comes into the interface of switch 1 here, before it decides to forward the traffic out the next interface, what it's going to do is it's going to look at the source of the traffic that was originating it from. And with the RPF, it's going to be checking, is this the same path that I would follow to get back to the source? This is the reverse path, going in the reverse direction. Basically, if this were a unicast traffic, is this the path that I would take to get back to the source? That's kind of the gist here that we're talking about. So the gist of it is that if this packet were to come up to switch 2 and then over to switch 1, when switch 1 looks at its routing table and it says, to get back here, I would not send my traffic to switch 2, switch 1 is then not going to forward that information out all of the other interfaces. It's not going to happen like that. So this is critical to understand when it comes to deploying and troubleshooting a multicast network. Lots of times, multicast information doesn't come to life. Multicast routes don't actually enter the routing table or the multicast routing table because it doesn't pass the RPF check. Sometimes the multicast stream may only come in on an interface that it wouldn't use to return back. So if we only enable multicast on one interface, and that one interface isn't the optimal interface for return traffic, guess what? It doesn't pass the RPF check, and as a default mechanism within multicast, it stops that traffic from being forwarded to the next hops in order to prevent loops. So this is why in that initial nugget I said it's very important to have an IGP like OSPF, ISIS, or EIGRP deployed throughout your network and operating in a stable manner, because this is how multicast is going to determine what is the best path for me to get to the source and does it pass the RPF check. That way we don't create multicast loops within our environment. So this is understanding how RPF plays a role within multicast, and it prevents loops and makes sure that we have the optimal path going back to sources. I hope this has been informative for you, and I'd like to thank you for viewing. So there you have it. That is the foundation of how multicast works within an enterprise network. In the next skill, we're going to dig deeper into this and talk about the actual protocols that are used to deploy multicast throughout our enterprise. But now you understand the basics of how the RPF check actually stops loops, how we can build different types of tree structures to actually forward multicast traffic throughout our enterprise. We even understand IGMP a little bit and how that initiated stream begins, or the request to receive a stream begins. I hope this has been informative for you, and I'd like to thank you for viewing. Multicast in the real world is not a simple thing to design, deploy, operate, and optimize. That's why in the previous skill, we laid a foundation about the inner workings of multicast. What is a source tree? What is a shared tree? Now it's time to focus in on the actual protocols themselves and how they can be designed and manipulated to work specifically within our enterprise. Within this skill, we're going to cover the different flavors of IGMP and the different flavors or deployment methods and designs for PIM itself. This is going to be a huge skill. Again, if you're brand new to multicast and you still feel a little bit fuzzy on the multicast foundation, I'd encourage you to watch those multicast foundation nuggets again or for the first time before you dive into this content, because this content right here is going to be critical to understand if you're going to be designing and deploying a enterprise network with multicast, or if you're taking the ENSLD examination. So get ready, because this is going to be one whopper of a skill. Let's get going. We know from our multicast foundations that IGMP is the starting point for initiating a multicast session or receiving a multicast session. But IGMP has evolved a lot over the years, and now there are 3 different versions of IGMP. So what we need to do in this particular nugget is talk about what the evolution of IGMP is and how it's really working under the hood. Let's get going. So it's time to talk about IGMP and the 3 different versions of IGMP and their evolution over the years. Quite frankly, at the end of the day, there's not a whole lot to IGMP. It just kind of works, and it's kind of magical in its own way. But it has evolved a lot, because remember, multicast has really been around since the 80s. And as the networks themselves, the physical components and the speeds change, IGMP and a lot of other protocols that we work with have to evolve with it. So it all started out with IGMP version 1. And the gist of IGMP version 1 works kind of like this. We have a desktop down here in the bottom right-hand corner of the screen, and it wants to join a group. It wants to receive traffic that may be destined to the group address of 231.1.1.1. So we know from our previous skill, this is kind of something like a star, comma, G. We don't know where the source is, but we do know what the group is that we want to join. So what our desktop does is it creates an IGMP join request. It creates this packet and it sends it to its default gateway. And as long as its default gateway, which in this case is switch 14, is participating and listening for multicast addresses, it will receive that and it will know, I have someone on my local segment that I want to send multicast traffic to. The real important thing to know about IGMP in this particular case is the default gateway, switch 14 in this case, doesn't recall that it's desktop 26 that it wants to send traffic to. It just knows that it has a member somewhere out there that it needs to send multicast traffic to. So in this case, if this desktop had the IP address of 192.168.2.26 and the default gateway was .1, what will end up happening is the default gateway, when it receives multicast traffic destined for that, it will send that multicast traffic out to all the hosts on that particular Ethernet segment, because all it knows is that someone has requested traffic towards that group. It doesn't remember who specifically it was. Now, there is a fix for that, and we're going to talk about that at the end of this nugget. At this point, we're still only talking about IGMP version 1, and we've covered the request to join a particular group. This switch, switch 14, now knows that it has a request for that particular group. And what it will do periodically is it will create a query every so often asking if anyone on that Ethernet segment still wants to receive that traffic. This happens periodically. So if desktop 26 still wants to receive this traffic, it would have to reply, yes, I'm still expecting to receive this traffic. Otherwise, after a dead interval occurs, switch 14 would then send a prune request back up to its neighbor saying, I no longer want to receive this traffic. Do you see where the pitfall about IGMP v1 occurs? The pitfall here is that the moment that desktop 26 is ready to stop receiving traffic, it doesn't stop receiving traffic. Traffic is still sent all the way out to this device, and it has to process and drop these multicast packets until the dead interval occurs. And this is where it's like, wait a minute, we're wasting a whole lot of bandwidth. We could go minutes receiving traffic that we don't actually need or care about anymore. And that would waste and choke a lot of bandwidth throughout the entire enterprise. Enter IGMP version 2. This built in the mechanism that's added on to IGMP version 1 that allowed desktop 26 to communicate to switch 14 that it was ready to leave the group. Now recall again, this is a major talking point about IGMP. Switch 14 is not keeping track of which hosts on its Ethernet segment all want to participate in the group. So when it receives a one leave request from one of the items on its Ethernet segment, it then generates a query to see if anyone else on the Ethernet segment is still wanting to receive this particular traffic. So if I kind of clean up the screen here just for a moment, if we had multiple hosts wanting to receive this traffic, desktop 26 could send its leave request to its default gateway on switch 14, which switch 14 would then trigger a query to see, does anybody else still want to receive this traffic? Either of these hosts could reply yes, and the stream would still continue to be sent to all the devices in that particular segment. It's not until all of these devices stop replying to that query that the switch stops sending the traffic. But the good news is at least we have a mechanism to initiate a query quicker than on that interval. And that could greatly speed up the leave process whenever everybody is ready to stop receiving the multicast traffic. Now, our last item that we have to talk about is IGMP version 3. And what IGMP version 3 did is it added the ability to carry traffic for source-specific multicast. That's really the only improvement that IGMP version 3 brought to the table, and we won't really talk about this more until we get into specifically source-specific multicast. Well, that's a lot of specifics there, isn't it? When we get into source-specific multicast, we'll then see, oh, okay, this is how it's all actually working. Now, there's one drawback that we've still talked about up till this point, is that switch 14, the default gateway, doesn't know who is sending in the traffic. All it knows is that someone has created a star comma G, therefore people on this Ethernet segment want to receive the traffic, so I'm just going to send multicast traffic out to everybody. There is an RFC standard protocol that was created to fix this, and that is IGMP snooping. At layer 2, when desktop 26 creates this IGMP join request, the device, the switch that is performing IGMP snooping, will actually sniff out this IGMP request and create the MAC address entry in its table to automatically remember who are the members that have requested multicast traffic to be sent to it. That way, multicast traffic isn't actually flooded throughout the entire Ethernet or VLAN segment. It will remember specifically who created the IGMP request and then only send the multicast traffic to those specific hosts. So IGMP snooping is what solves the flooding scenario when it's time to send traffic to the end devices on the local Ethernet segment at layer 2. So this is the deep dive into IGMP and the evolution that it's created over the years. We've got IGMP v1, which created a little bit of a problem because we had to wait for a dead timer interval to expire before we stopped sending traffic to all the hosts. Then we had IGMP v2, which created the mechanism to start a query process by requesting to leave a group. IGMP v3 was primarily created to handle source-specific multicast, and then IGMP snooping allows our layer 2 segment to remember who has requested to join a specific group rather than flooding the traffic to all the devices within a VLAN. I hope this has been informative for you, and I'd like to thank you for viewing. Understanding the concept of the source tree or the shortest path tree and where it would fit in those densely populated environments, this is where we can start to transition into how to deploy PIM for that specific design consideration. This is called PIM dense mode. And in this particular nugget, what we're going to talk about is one of the original flavors of PIM, which is where we would deploy PIM dense mode and how that would really operate under the hood. Let's get going. So the first PIM flavor that we are going to be talking about is the easy one, PIM dense mode. But here's the real kicker. PIM dense mode is not deployed in very many scenarios because it consumes a tremendous amount of bandwidth and overhead throughout the network. Again, what we're really talking about here at the end of the day is the source tree or shortest path tree scenario. I'm going to put SPT here for shortest path tree, and know that many texts or exam scenarios themselves may abbreviate this to shortest path tree to SPT. In this case, let's pretend we have a desktop here that wants to initiate a stream. It wants to send traffic into the entire environment. And let's now pretend further that this is going to be a high bandwidth intensive stream, something like 4K video game streaming at 60 frames per second. This could consume as much as 100 megabits per second if it's not left unchecked, if there's nothing to limit it, because, well, that's just what video game streaming can do these days. So it's going to send in this stream into the network, and the source tree is also what PIM dense mode is all about. The IGMP stream gets initiated, and then with PIM dense mode is all about, I'm just going to send this stream to all of my neighbors, out all of their interfaces, and it's on them to figure out whether or not they want this stream. When they receive this stream, they can either accept it and forward it on to the next host, or they can send a prune request saying they don't want this stream. But the idea with PIM dense mode is that we're punting this stream out into the entire environment because we expect that most hosts or most devices running PIM want to receive this stream in the first place. In reality, that's not what really occurs in most enterprises. Most enterprises have sparsely populated or located recipients, and this is just an awful lot of bandwidth consumption at the end of the day, and that's why most devices don't run PIM dense mode. But again, the idea with PIM dense mode is that these switches will receive, these endpoint hosted switches will receive this traffic, and if they do want to receive this traffic, they will find the shortest path through the network back to the source and then send prune requests out all other links. That way they don't receive this traffic on too many links and it chokes up too much bandwidth. They will quickly identify, I do want this traffic, but I only want it to come from this link because that is the shortest path based on my reverse path forwarding table. It's going to look at the source of this desktop right here and say, my unicast table says the quickest way for me to get to you is through that interface. So that is the interface that I want my multicast traffic to come from. So the big takeaways with PIM dense mode is that PIM dense mode really has two technologies at play here. The first one is the shortest path tree, which is driven by the second one, the reverse path forwarding check. The drawback to it is it consumes more bandwidth than is oftentimes necessary. Now, for the most part, if you're here because you're studying for the ENSLD exam, you do not need to know multicast configurations. However, it is really nice to see these types of things in action. That way, when you have your own lab environment, you can practice these things and drill these concepts home. So very quickly, what I'm going to do is I'm going to bring up the terminal of switch 14 and switch 5 and illustrate what a PIM dense mode configuration would really look like. We can see here the link that I'm talking about is Ethernet 1.1 on switch 5 and Ethernet 0.1 on switch 14. If desktop 26 sends in the request to join an IGMP group like 231.1.1.1, switch 14 then needs to form a PIM neighborship to switch 5. That way, switch 14 can say, hey, I have a star comma G of 231.1.1.1. If you get an S comma G, meaning you know of a source for 231.1.1.1, I want it. So the configuration looks something like this. In configuration mode, we first have to turn multicast routing on, and that is done with IP multicast routing. Huge talking point already if you're thinking about going for the CCIE examination someday. When I hit enter right here, this turned on multicast routing and a multicast routing table for the global routing table. This does not turn on multicast routing for specific VRFs that I may have in my environment. See, if I hit question mark, I have the ability to turn on multicast routing within a specific VRF. So just know that multicast routing, turning on IP multicast routing, doesn't turn it on absolutely everywhere if you have VRFs running. But at this point, multicast routing is up and running on my entire environment. So at this point, if I want to turn on multicast routing on all of my interfaces for this particular switch, I may say interface range Ethernet 00 through Ethernet 02 and Ethernet 10 through Ethernet 12. Oop, got to put that E in there. And then I'll say IP PIM and press question mark, and you see we have a bunch of different options available to us. The big ones that I want you to pay attention to are dense mode and sparse mode. We're going to talk about sparse mode in the next nugget. Don't worry about that right now. But know that this is where you go to configure them. I'll put on dense mode here to enable dense mode. And do you see what happened here? Interfaces that had IP addresses came up running IP PIM dense mode. Now over on switch 14, I'll perform the exact same actions. I'll turn IP multicast routing on. Then I'll say interface range, Ethernet 00 through 2, comma, Ethernet 10 through 1, and I'll say IP PIM dense mode. Ah, look at what we have here. A neighbor adjacency has formed, and at this point, we now have IP PIM dense mode deployed within our environment. I can now perform show IP mroute, which is how we actually look at the multicast routing table. And we automatically have an S, G already up and running. This is destined for 224.0.1.40, which is actually for auto RP discovery. Whenever you turn on multicast routing and enable a PIM interface, this entry will automatically be populated in the multicast routing table, and this is how you know multicast routing is actually up and running in your environment. So at this point, all we have to do is deploy this configuration on all of the other interfaces, on all of the other devices in our environment, and we have successfully deployed PIM dense mode. Then the last thing that needs to happen is a stream of data needs to come into the environment, and PIM dense mode will take over from there and create the shortest path trees back to that source. So that's been understanding PIM dense mode and how it uses a source tree with reverse path forwarding. I hope this has been informative for you, and I'd like to thank you for viewing. Next up, it's time to talk about when we have sparsely located endpoints or clients that are wanting to receive a multicast stream and how we can deploy PIM for this particular design. This is called PIM sparse mode. Now, here's the kicker to it. There is some little trickeration that happens at the end. We're going to be talking about the deployment and position of the rendezvous point, but then the real spoiler here is there ends up being a shortest path tree anyways. This is a critical thing to understand, is when there is a shortest path tree and when there is not a shortest path tree in your multicast design environment, and that's what the remaining nuggets are also going to be talking about. This is the first flavor of a sparse mode deployment called PIM sparse mode. Let's get going talking about that. Now it's time to talk about the more commonly deployed flavor of PIM, and that's PIM sparse mode. This is where we have a source and then maybe a few endpoints or a few recipients rather than densely populated recipients. And as we talked about before, this is what's going to typically use a shared tree. And when you see shared tree, you should be thinking of rendezvous points, or more commonly abbreviated to RP. In fact, all the commands are basically going to say RP instead of rendezvous point. So know that RP, rendezvous point, they're synonyms to each other. Again, we've got this scenario where maybe we have a source down here and a destination down here, but we don't want to flood this traffic all over the place. So what we do is we tell our PIM participating routers, just meet at one central location. That way you can figure out the best path to each other from there. So if we say switch 1 is going to be our rendezvous point, what we're now doing, when desktop 25 initiates the stream of traffic, what it's going to do is it's going to say, hey, wait a minute, I know there's a rendezvous point, and my rendezvous point is the loopback address of 1.1.1.1 here on switch 1. So it looks in its routing table and it finds that this path may be the best path to get to 1.1.1.1. So it sends its S, G traffic towards this particular location. It encapsulates a packet in a PIM request that says, hey, here is a new source of traffic, and it sends it to switch 1. Down here over on desktop 26, it creates its IGMP join request, which is the star, G. It sends it up to switch 14, and switch 14 has also been configured to know about the rendezvous point. So rather than flooding the star, G to all its neighbors saying, hey, I'm looking for this traffic, it sends its traffic up towards switch 1 that says, I'm looking for this. Switch 1 then handles the transfer of the S, G back down to the star, G device down here on switch 14. This is where it gets really, really interesting. The flow of traffic could continue like this if we wanted it to. We could continue to send source traffic to a rendezvous point, and destination traffic from the rendezvous point could be routed back down towards all the receiving destinations. So we could say the same thing about a host here on switch 11. It could send the traffic from here, then over this link here to switch 1, and switch 1 would handle sending the traffic back down. And that would still be an efficient use of bandwidth because you're looking at all of the other links that we haven't highlighted yet. Those aren't being choked out the way they would be in a dense mode populated scenario. But the real kicker, the real magic that Cisco implementations of sparse mode do at this point, once switch 1 has sent the source traffic down to the switch will then use RPF again to find a shortest path tree back towards the source. So the rendezvous point only is a helper that helps endpoints find where a source is at first, and then from there, the destination endpoints, these switch 14 and switch 11, will perform a shortest path tree calculation and construction from there. So the crazy thing about all of this, if I clear the screen, is it starts out with a rendezvous point like this, where the source, G, the source traffic goes to the rendezvous point, and the star, G, the request for traffic, goes to the rendezvous point. But once traffic has now been sent back to switch 14, and switch 14 knows of the source, it's going to take the most direct path to get to the source from there on out. So when we talk about PIM sparse mode without any other flavors, you should know that it starts out as a shared tree, but it ends up as a shortest path tree. Now again, there's some other things that you need to consider that we talked about in the previous skill. How the rendezvous point is created by default. Well, there is no default creation of a rendezvous point. You can either manually assign a rendezvous point on every single device in the entire topology, including the rendezvous point itself, or you could perform some sort of automatic RP creation and discovery. Those were using the flavors of Auto RP, which is the Cisco proprietary, or Bootstrap Router, which is the open standards one. Again, configuring these items isn't actually a topic of the ENSLD exam. This would actually be getting more into the CCIE level preparation, is how to configure these types of things. All you really need to know about is how the operation of PIM sparse mode really operates, and we've covered that up till this point. But with that being said, it is nice to see these things in action, isn't it? So I've got the terminal of switch 1, switch 5, and switch 14 brought up. That's switch 1, switch 5, and switch 14 brought to life. What I'll do very quickly on switch 1 is I will enable IP multicast routing, and then on all the interfaces, I'll create my interface range, and then I'll also throw in loopback 0, I'm going to enable IPPIM sparse mode. But then I'm going to take it a step further, and I'm going to tell this device, you are the rendezvous point. So I'll say IPPIM RP address, and say that the RP address is my loopback address of 1.1.1.1. Looking at any other options, I could specify things like an ACL that would tell it which groups are you the RP for, and that's what these first three options are for. We could also override any RPs that we've already learned about, but I don't need to do any of that. I'm just going to statically tell this device, you are the rendezvous point for sparse mode, just like that. You can see it creates these interesting tunnel interfaces, and that's how the rendezvous points actually communicate to each other. I'll exit out of configuration on switch 1, and I'll kind of do all the same things over here on switch 5. Let me give it a show IP interface brief. I'll go into configuration mode. I'll say interface range, Ethernet 00 through 3, and Ethernet 10 through 1, and loopback 0. I'll say IPPIM sparse mode, and then I'll exit out and statically assign that rendezvous point again with IPPIM RP address 1.1.1.1. Lastly, I'll do the same thing on switch 14. Let me give it a show IP interface brief so I know what IP addresses I'm working with here. I'll go into configuration mode. I'll say interface range Ethernet 00 through 1, loopback 0, and VLAN 88. I'll say IPPIM sparse mode to turn it on, and I'll set the IPPIM RP address of 1.1.1.1. Now's where we're going to have some fun. I'm going to pretend for a moment that switch 14 wants to receive some multicast traffic. So how do we do that? Recall, we create an IGMP join request. I'm going to go into interface loopback 0, and I'm going to say IP IGMP join group, and then I want to join 231.1.1.1. This is actually going to create the this is going to create the join request for 231.1.1.1. And it's going to create the star comma G and send that information to all of its IPPIM neighbors. So now if I exit out of configuration mode and I do show IP mroute, we can see right there I have my star comma G for 231.1.1.1. If all went well, this request to join a group should have been sent up to the rendezvous point, so the rendezvous point is now listening for 231.1.1.1 traffic too. So let's go to switch 1 and do show IP mroute. Ah, look at that. We now have the star comma G that's located on the rendezvous point 231.1.1.1. Beyond that, on switch 14, I can say show IP PIM RP mapping. The cool thing here that we notice is that we know that our rendezvous point of 1.1.1.1 is for the all groups. We haven't limited it to a specific group, but we see that we now have connectivity to our rendezvous point. It knows that the rendezvous point is there. So now let's have some real fun. What I'm going to do on switch 5 is I'm going to initiate a stream of traffic to 231.1.1.1 sourced from loopback 0. My expected behavior is that this initiated stream will go to the rendezvous point, who will then send it back to the host that it's expecting to receive it. That was our loopback address on switch 14. At some point, switch 14 will respond to the ping request. And there it is. Our reply comes back from the loopback address of 14.14.14.14, which is where we initiated the IGMP join request. That is how PIM would actually be deployed in the real world with a sparse mode deployment using a rendezvous point. I hope this has been informative for you, and I'd like to thank you for viewing. Up until this point, we've talked a lot about a scenario where there's one sender and multiple recipients, and that is the entire point of multicast. But what if the direction of our multicast streams was bidirectional, meaning one sender could send to many recipients, and then many recipients could send to many other recipients, or back to the sender. This is where we need to talk about a bidirectional PIM deployment, and this is kind of a flavor of sparse mode. Now, the big kicker, the big spoiler about bidir PIM, as it's very frequently called, is that it only has a shared tree. There is no shortest path tree deployment, and that is a major talking point that you should drill into your head, especially for an exam environment. Let's get going talking a little bit more about bidir PIM. Now, the last few nuggets on our multicast journey are going to be theoretical in nature, but they are real-world deployments that you need to consider when you jump into expert-level multicast deployment throughout an enterprise. When we talked about the shared tree in PIM sparse mode, what was the big thing that really kind of made you go, oh, wow, that's pretty cool? We go to a rendezvous point, just like we did here, traffic source from over here, destined for over here, starts at a rendezvous point, but then at some point, they build the shortest path tree to each other, and the rendezvous point gets completely cut out of the picture. What if there's a scenario where we don't want that to happen? What if we want traffic to always traverse through a rendezvous point because we find that this is going to be an efficient way to make communication happen? How would that really be the case? That's usually the case when we have bidirectional flows of traffic and multiple hosts located throughout the enterprise that are participating in multicast streams. It could look something like this. Our rendezvous point would then be a pretty dedicated piece of hardware to doing nothing but being a rendezvous point. That's something to keep in mind here. But this is still a very efficient usage of bandwidth because we don't have necessarily just one source with a few endpoints throughout the network. We could have multiple sources that are communicating back and forth to each other using multicast streams. What we call this is bidir PIM, and that's short for bidirectional PIM. The thing about bidirectional PIM is it is a sparse mode deployment, but it does not have a shortest path tree calculation. It doesn't end up on that. It maintains the rendezvous point, and the rendezvous point, as well as all of the nodes participating in this, know that this is a bidir PIM deployment. You do have to explicitly configure it to be a bidir PIM deployment. So whether you're in the real world or in an exam environment, the big takeaway from this short and sweet nugget is that bidir PIM is a sparse mode deployment of PIM, but it maintains the rendezvous point rather than building a shortest path tree. So that's what you need to know about bidir PIM. I hope this has been informative for you, and I'd like to thank you for viewing. One of the newer flavors of PIM is called source-specific multicast, and this is where we do have a sparsely populated endpoint or receiver scenario, yet we also know exactly where the source is coming from, and there's really no point in having that overhead with a rendezvous point associated with it at all. We could actually request to join a group, and we already know where the source is coming from, and that's the entire point of source-specific multicast. Let's talk about how SSM, or source-specific multicast, really works under the hood. The next flavor about PIM sparse mode that we're going to talk about is one of the latest flavors to come about. It's still kind of old, but it's one of the newer ones that you should know, and that is source-specific multicast. Now, this is what we're going to do. We're going to contrast bidir PIM to source-specific multicast because they kind of go in the exact opposite direction here. Recall in the previous nugget, the entire point of bidir PIM was that we were going to have bidirectional flows from multiple hosts throughout the network. And the efficient way to use our bandwidth in this case was to keep it going through a rendezvous point. So in bidir PIM, we don't use a shortest path tree. We just have bidirectional flows that traverse through our rendezvous point. Source-specific multicast kind of goes in a different direction. In this case, when this host is ready to join the group, it already knows the source that it wants to get traffic from. So rather than going through a rendezvous point, it just tells its gateway goes straight to the source, and it builds a shortest path tree straight to the source. In other words, in source-specific multicast, there is no rendezvous point. This works really well when the source is a well-known source. It is a dedicated source for streaming information. This is primarily used in like service provider technologies or even television technologies where they're going to be constantly streaming a feed of data or information or television shows or athletic events or things like that. If we know that this host right here is always going to be streaming data or information, there's no reason to use a rendezvous point. We could tell our host, hey, I want to join this group and I want to specifically join it from that particular source. So the big contrast here is bidir PIM was all about keeping traffic going into the rendezvous point when we have sparsely populated endpoints, but they want to send data back and forth. Source-specific multicast is we still have sparsely populated hosts. There's no reason to do dense mode and choke up traffic through our entire topology, but we also know exactly which source we want to come from, so there's no point in going to a rendezvous point in the first place. This could also work well if we have multiple sources and we actually want to load balance some traffic. Maybe desktop 26 gets its traffic from this source, and this host over here on switch 11 gets its traffic from this source right here. So the big takeaway with source-specific multicast is it's still a sparse mode deployment, but there is no rendezvous point because we already know exactly what source we want to go to. So when we create our IGMP packet, we say just go straight to this particular source, and that's why IGMP v3 was created. Instead of creating these star comma G, IGMP v3 was created to handle I want to go specifically to this source. It was basically a join request to an S comma G. That's how IGMP v3 was really created, and that's what source-specific multicast does. I hope this has been informative for you, and I'd like to thank you for viewing. Now, up until this point, we've talked about one large enterprise campus and how multicast would behave on that campus. What happens when our enterprise is around the entire globe, and all of a sudden we have different administrative groups or administrative teams working on each of their own enterprise campuses? Maybe we have a site in California and a site in London and a site in Tokyo, and different teams manage those. Well, guess what? We have different multicast domains at that point too. Now, there could be a situation where we want one multicast stream to span across the entire globe, and this is where MSDP comes into play. This is where we have multiple multicast domains coordinating and communicating to each other. Let's talk about how MSDP could save the day when we have a very large enterprise environment. Our last technology that we should talk about is an exciting but kind of complicated deployment scenario. And again, it's not one that you really need to know much about until it's time to get into your CCIE studies, but it is MSDP. We kind of set up what this scenario was all about, and that's when we have multiple multicast domains. Up till this point, we've talked about this single multicast domain where we have an S comma G, a source coming from here, and a star comma G, a request to join that source coming from this desktop over here. In a sparse mode deployment, we'll still have a rendezvous point, unless of course it's source-specific multicast. But pretend for a moment that this is a traditional PIM sparse mode deployment. So we send our traffic up to the rendezvous point, just like this, and this is our single domain of multicast. But what happens now when we have another domain of multicast separated by the internet over here? Maybe we have tunneling technologies or a Metro E or an MPLS technology that's connecting these sites, but over here we have another rendezvous point, and we have a series of hosts who want to receive traffic that is being originated from this source. What we need to do is we need to get our rendezvous points in communication with each other. And that's what MSDP does. MSDP is the protocol and the technology suite that is used to make rendezvous points share multicast routing information between each other. Now here's the real kicker. There's tunneling technologies and WAN technologies that often separate these rendezvous points to each other, and it's often not enough to just enable MSDP and have them start sharing routing information to each other. Oftentimes we have to actually run a routing protocol between these two rendezvous points, and really important, that routing protocol needs to be able to transmit multicast routes to each other, not unicast routes to each other, and that's why MSDP is often deployed with multi-protocol BGP. Multi-protocol BGP is exactly what the name says. It's BGP that can handle multi-protocols, so it could use IPv4 unicast, IPv4 multicast, IPv6 unicast, IPv6 multicast, VPN v4, and it can do all of these things within VRFs too. So what you need to know if you're going into an enterprise design multicast environment for the first time, or if you're going to take the ENSLD exam, is you need to understand that MSDP exists to link multiple multicast domains to each other, and it enables communication between rendezvous points so they can share S, G's or star, G information to each other. And that multicast traffic is often carried between sites or domains by multi-protocol BGP. So that's been understanding MSDP and how it really works in a global or large campus environment. I hope this has been informative for you, and I'd like to thank you for viewing. So that wraps up our journey through multicast design. If you followed along in the previous skill with foundations and through this skill, you've seen now what kind of a major journey multicast could really take you on at the end of the day. You've learned things about how the multicast stream is initiated and how multicast routing actually occurs, how multicast packets can make multiple hops. Then beyond that, we have to design our network for bandwidth efficiency, scalability, and stability, and that's where the different flavors of PIM come into play. There's dense mode, there's sparse mode, which still has a shortest path tree. There's biter PIM, which doesn't have a shortest path tree. Then there's source specific mode, which only goes straight to the source via a shortest path tree. It's kind of crazy, all these different scenarios and options that we have at the end of the day. So I'd really encourage you to watch this content as many times as you need to let this digest, because it's very important for large enterprise campuses as well as the ENSLD exam environment. I hope this has been informative for you, and I'd like to thank you for viewing.